everyone. I hope that everyone can hear me. So, as Andrew introduced, I will talk about astrochemistry. And before we draw some real links between galaxies and bars, I will actually explain to you what is astrochemistry and what I work every day. So, okay, astrochemistry, what is that? Maybe you've heard about astronomy, astrophysics, but what is astrochemistry? And before I go on, just this little guy, oops. Okay, this little guy is called the Bouvier, if you don't have the reference, and this is very important for the photo. So, in astrochemistry, I have to know where I should point. Okay, astrochemistry, of course, there is the part of astro, because we are studying the object of the universe, whether it is the comets in our solar system, forming planets much further away from us, but still in our galaxy. We are also studying the death of planets, like the supernova remnants that you can see on the left corner. And we also study galaxies in my case. And to do that, we are using a molecule, so where this is called the chemistry part of the word, because in our universe is not empty in the interstellar medium, so literally the space between stars is not void, there is gas and dust, and this is where molecules are happening there. So how can we observe molecules? So we are looking at two main frequency ranges as astrochemists. The first one is the radio domain from centimeter to millimeter wavelengths. This is where most of the molecules have been detected and are today observed. And we can observe them from the ground because the atmosphere is transparent, so we are not bothered by the atmosphere, so we can observe them from the ground. And the emission that we receive from these molecules is actually their movement. So in the radio frequency range, they have what we collect is their rotational transition, what we call them. So this is an example of CO2 that rotates into different directions. And when they do this movement, we detect their frequency range in the radio domain. The other one is in the infrared domain. Here, at a longer, smaller wavelengths, and here we have to send a probe in the space because the atmosphere is quite opaque. So we are bothered by the atmosphere, so we have to launch and observe the molecules outside of the Earth. And in that frequency range, the molecules have a different movement, so we call them the vibration transition, and sometimes it's a mix between vibration and rotation, so we call them rotational transitions. But depending on how the molecules are moving, basically, we detect them either in the radio domain or in the infrared domain. So here is an example of the telescope that we can use. So in the radio domain, we use a radio telescope. So either with only one antenna, we call them a single dish telescope, or with a collection of antennas, which are called interferometers, and you can see that there are several across the world. And with them, we are looking at the molecules that are in the gas phase, and we are looking rather at the cold interstellar medium. If we go to the infrared domain, so with the probes here, so maybe you heard about James Webb Space Telescope, and before that Herschel, we are looking at a warmer interstellar medium, and we can see the molecule both in the gas phase, but also on the ice that is settled on the grains. But tonight, the talk, I will focus more on the radio domain, so what we see in the gas phase. So let's take, for example, my pet galaxy, NGC 253. It is a very nearby galaxy. It's very active in the center. There's a lot of high mass stars being formed there, so we call it a starburst galaxy. And basically, if we look at the center of this galaxy with a telescope, a radio telescope, it captures the frequency of the molecules that are rotating. And then, from what we have, we actually get this spectra. This is called spectra, so it has intensity as a function of the frequency. And each of the peaks actually can be associated with one molecule. So this is a bit of spectroscopy, but basically we can retrieve back which molecule emits at which frequency. And you might see that, for example, this molecule appears 2 times because molecules have different energy levels, so they can be excited, let's say, in a different way, and so they are going to emit at different frequencies. So this is what we did. Now, when we observe molecules in galaxies, it's not quite simple. In galaxies, so we have a lot of different components, and here is an example of what we can probe. For example, if we look at a galaxy with the radio telescope, so we have different phases with different densities and temperature. For your reference, I put here the density you can find on Earth, and some correspondence with the degree Celsius. We can find diffuse gas, which is relatively not really dense. H2 regions are these regions that are powered by massive stars. So the massive stars are radiating around them, they are heating the surrounding interstellar medium, and they are ionizing it. So this is called H2 regions because hydrogen is in H plus form. Molecular clouds are one of the densest places in the interstellar medium where stars are forming within them. But basically, when we observe at the galaxy, everything is mixed together. So we don't have really, we cannot really say what component of the ASM is there. And what we do to understand how the structure of the regions that we are observing in the galaxy is, we are using molecules. Think about if you are looking with your binoculars at a group of minions that are over there, you don't have the vision enough to see which minions are there. So what is going to help you distinguish them is the color. For example, you know that the evil minions are purple, while the regular one are yellow. So if you see a purple spot, then you will know that there is an evil minion there. And you know that Bob is one of the minions that always has this teddy bear within, which is brown. So if you see a brown spot, then you know that Bob is there, and you can see if Bob is near or far the purple minions. This is the same with molecules. Depending on which molecule we are looking at, we know how the components of the ISM are gathered together inside the galaxy. Let's take a more concrete example. So if we look at CO, one of the most abundant molecules in the dense interstellar medium, after H2, of course, but H2 we can see it in the radio domain. So CO, you can see the emission of CO towards the center of this galaxy. It's quite extended from spectroscopic level and so on. We know it traces this kind of average density gas. It traces the bulk of the molecular gas. But if we look at another molecule, HCO+, for example, the emission is going to be different. It's more compact because this molecule traces a much denser environment, a bit denser. And so we know that we have a kind of a diffuse medium inside which there is a bit more dense medium. And let's take another molecule, SiO, which is going to be even more compact in its structures. It's because SiO has a silicon atom that are typically constitute the grains. So the only way to have silicon into the gas phase is if your grain is broken. So you need shock. So if you see SiO, it means that there are shocks within the galaxy. And usually it traces much higher temperature compared to CO and HCO+. So by looking at the spectra, we can really reconstruct the physical structure of the galaxy. So we have our CO that is quite large, and then HCO+ tracing the more dense parts, and we know that there are shocks throughout the center of this galaxy. Now, tonight I wanted to focus on the most exotic molecules, what we call them the complex organic molecule. So if you ask a chemist what a complex molecule is, he's going to tell you DNA is complex. There's more than 150 billions of atoms. But for us, we just need 6 atoms, and for us it's already complex. The simplest one is methanol, so CH3OH. And there are other complex organic molecules that we like, which have a nitrogen atom, a carbon atom, and an oxygen atom. And this is called a peptide-like bond. It is very important if you want to produce amino acids themselves important to produce proteins. So basically we like COMs, complex organic molecules, because we think they are the building blocks of the molecules important for life on Earth. So we are happy when we see them. And we actually can detect them in a wide range of environments, whether it is in comets and asteroids, in our own system, solar system, in forming stars inside our solar system, molecular clouds, and so on. But what is interesting is that the more complex the molecule, the fainter the emission is going to be. And yet, we see them in nearby galaxies. So this is galaxies that are, for us, not too far. So the redshift is 0. If you want the equivalent in megaparsec or even kilometer, you can see. But these are an example of galaxies where we detected complex organic molecules. And even more interesting is that we see them in higher redshift galaxy ones. So for me, it's high redshift, but for high redshift astrophysicists, it's not high redshift, but for me it is. And so it is amazing that we can see these building blocks for life such far away in the universe. Now, it is important to know that if you want to understand what the molecule is telling us about the environment that we are looking at, we need to understand how they are formed in the interstellar medium. For complex organic molecules, these things move without we don't know really how they form. So there is two different ways. As I mentioned, in the interstellar medium, we have gas and dust. And in the denser region of the interstellar medium, the dust is covered in ice, which allows chemical reaction to happen. So the first way to form an icon is on the gas phase. So you have two simple molecules that are released from the brain. They are going to meet and form a complex organic molecule. There it is. No? Yes. The other way to form a complex organic molecule is directly on the ice. So the two species are going to meet on the ice, form the complex organic molecule, and then release it into the gas phase where we can observe them. In both cases, in order to release these complex organic molecules or to form them, we need either a very hot environment, I mean hot for me, but 100 Kelvin is quite hot for me, and a shocked environment. So, when we come back to our galaxy, M653, this is the structure that we had in mind until now. We detected up to 5 complex organic molecules. So, if you are interested by the name, so first you have methanol, and then methanamine, formamide, acetaldehyde, and ethanol, which is one of the most complex organic molecules detected in the interstellar medium. And what these molecules told us is that actually there are shocks, but there are two different kinds of shocks in that galaxy. Some of these icons were looking like the SIO emission, if you remember where the shocks are. So it probes the very strong and fast shocks. This corresponds to the shocks that the forming stars are creating, because when they are born, they expel some materials around them, which shocks the interstellar medium, and so it breaks the grains where we can see the molecule. And other complex organic molecules were not really similar to SIO, so the strong shock molecule, but they were located in a gas that is too cold for them to be able to form. So what we concluded is that they are also tracing shocks, but slower shocks. That is due to cloud-cloud collision, so when two molecular clouds are encountering and clashing in that galaxy. So thanks to these complex organic molecules, we have actually an even more complex view of the center of this galaxy. And now you can still wonder then what's the link with galaxies and bars? Well, I just told you that we detected methanol and ethanol, which are of course alcohol. But actually, ethanol is one of the most interesting molecules. Do you know in which beverage we find it?
Beer.
Yeah. Beer. We also detected acetaldehyde, and do you know in which beverage you find that?
Special beer.
Sorry?
Special beer.
Coffee.
Yes, coffee. So here is your astrochemical link between galaxies and bars.
Thank you very much, Mathilde. Do we have any questions from Jones? Yes?
So you talked a lot, by the way, nice talking very much. You talked a lot about these shocks, but in my mind, even though the universe is not empty, there's still something there, but they are far apart, it's not like super dense. Does this shock like propagate similarly to how I would envision, for example, a bomb exploding or something, or must I envision it different? So how does this shock even occur? What should I envision is happening in space?
So, yes. So the kind of shocks that we see here in the galaxy. So we know that we are looking at regions where there's a lot of stars that are forming. So the majority of the shocks, we can expect them to come from these stars forming, as I showed before, so with ejecting materials. Well, I don't know if I can go back, yes. Anyway, no, maybe not. Anyway. And the thing is that the galaxies inside, they can be formed with what we call a bar. So there is a bar of molecular gas that crosses the center of the galaxy, and this is what can create the cloud-cloud collision. So in that case, because we know the kind of environment that we are looking at, which is dense, we know it can be either of these possibilities. There is also the death of stars that can create shocks, but we didn't find any evidence of these shocks created by this death of stars in that galaxy.
But is then a shock a pressure wave just propagating to space, or is it like material?
So in that case, it's a grain that is destroyed by a wave that is, yes.
So there's like a pressure wave.
Yeah, I think you can.
Yeah, it's not really pressure as in you would expect on
Yeah.
Earth, of course. But
If you want to visualize it, it's like
some
a front gas and dust that is colliding with
yeah.
the rest of it.
Good, thank you.
Yeah.
So in the spectrum that you showed at the beginning, you mentioned some densities. Are these densities associated to the transitions? How do you relate, in fact, the spectrum to the density? Or do you know that from lab measurements, or does it come from the data?
So it's from the molecule itself. So it is, I think, from the spectroscopy. So we know that above a certain density, it can be excited by collision. So if the environment is dense enough for the molecule to meet, and if we know that it's enough for this particular molecule to be excited and to be seen, then we know what is the minimum density at which we can see that traced by this particular molecule.
And so this information comes from lab measurements?
Yes, I mean from not only lab measurements, but also in a general spectroscopy analysis, radiative transfer. I mean, it's a theoretical studies, but it can be. I'm not so familiar with what specifically comes from the laboratory and what's not coming from the laboratory.
Are these molecules universal? For example, specifically, do you also find them in the solar system?
Sorry, can you speak?
Are these molecules universal? Like, for example, do you also find them in the solar system?
Do you mean, do we see these molecules elsewhere?
Yeah. Also
Yeah.
Specifically in the solar system, do you see them?
Yeah, so I took this source as an example because this is the source I work on. But yes, we can see the same molecule in other environments. They are not necessarily telling us the same story as in that galaxy. It depends really one object from another. But we can see them in various different environments. So one molecule can trace different components. This is why we study several transitions of one molecule to understand specifically what it tells us. But yes, otherwise we can see them in a lot of different environments.
Yeah, you mentioned that the more complex the molecule, the more difficult you can see it. So how likely would it be there are lots of very complex molecules out there which we simply cannot see?
There is really an issue of sensitivity indeed. We are always trying to find what is the biggest molecule out there. So there are some regions that are more easy, that we favor to try to look for what is the most complex molecule there are. So for example, the center of our own galaxy, this is where most of the more complex organic molecules have been found, and we know that because we are limited by the instruments, if we have more sensitive instruments, it would be we should go look there if we want to find the biggest molecules. But we are at some point we are limited by the instruments.
The limits
Yeah.
of the machine. Yeah. Thank you.
I was thinking about this spectrum,
Yeah.
which frequencies are associated with atoms. But as we know, the because of the Doppler effect, the redshift, these frequencies tend to change.
Yeah.
How we estimate the distance or how we measure the redshift to calibrate this scale?
Yes, so this is more usually for higher redshift galaxy. Yes, indeed, we have a shift in frequency that we can calculate with the Doppler effect. So if we know the initial frequency of the molecule, where it should be at our position, and the speed of the objects we are looking at, or the distance, then we can retrieve the redshifted frequency. So.
Are there any more questions? I can't see.
Maybe I have one question. I think in the beginning of the presentation you talked about hot interstellar medium and cold interstellar medium. To me, interstellar medium sounds just like the cold vacuum of space, but there's a difference. Can you explain that a little bit more?
Yes. So when I mentioned that for radio wavelength we look at the cold interstellar medium, is that we are going to look at like the dense parts of the interstellar medium. So what is molecular clouds, star-forming regions, and the molecules that are excited there are probing temperature up to a certain threshold. That if we were looking in the infrared, it depends also on the object, but if we go to the infrared, we can have other molecules towards the same regions that are going to probe much higher temperature. So, because other molecules are present. So it is, on average, the infrared we have access to molecules that are giving us information about the hotter temperature compared to if we look at the visibility.
As a shorthand, say that like denser regions are hotter?
No, denser regions are cooler. Again, it depends. So, one of the, if you look at a molecular cloud, it's one of the densest. It's a cloud that is cold, very cold and dense. But inside this cloud, you can form stars. So the stars itself is going to be hot.
Yeah.
But if you want to look at the central part of the stars itself, you're going to go to the infrared. Closer to the star, you're going to go to the infrared. If you are interested about the surrounding of the star that is cooler, you're going to stay in the radio domain to probe the surrounding. It's a matter of understanding what you want to probe. But I hope.
I have no background in any kind of physics, so I think I get it. Based on
we can.
maybe we'll. Yeah.
I see one more hand there.
In the cool, dense locations where you find these organics, do you also find traces of nickel?
Traces of what?
Nickel.
Nickel.
Not
Because that would be a catalyst in a lot of UV.
That could be what?
With a lot of UV and nickel, you have a catalyst to create a whole spectrum of organics.
Yeah, but this is quite heavy elements, so I would expect it to be either in the grain, or I don't think we have observed any in the gas phase any molecule with that.
Not really catalytic researchers.
On the grain, maybe? Usually, I mean, no, I mean we are assuming that the grains are of silicate base, and then theorists that experimentalists that try to understand the formation of these icons use a mix of CO2, water, CO, but no night. But Francel can correct me after.
Okay, I think we'll leave it there. Thank you again to Mathilde.